All right, thank you for joining me. We're going to be talking about tables of equivalent ratios today. And really what we're talking about here is equivalent fractions. When we talk about the word ratio, we're really referring to fractions. So we're going to be looking at how to simplify those and how to organize based on the problem and what the problem is asking you to do. So first of all, equivalent ratios, fractions that are equal when in simplest form. So we can see here with our examples at the bottom that we have 50 over 100, which we know can also simplify to 1/2. Or if you're looking at 6/8, we should know that that simplifies to 3/4. As a reminder, to simplify a fraction such as 50 over 100, you look at the two values and you determine what number can divide evenly into both of those, the numerator and the denominator. So we can see that in this case, we know initially 10 can go into both of them. When we divide 50 by 10, we get 5. When we divide 100 by 10, we get 10. But we can't stop there because that wouldn't be completely simplified. 50 over 100 equals 5/10. Those are actually equivalent ratios or equivalent fractions as well. But in simplest form, we can take that one more step and divide both 5 and 10 by 5 as well. So 5 goes into itself once and into 10 2 times. So this is a set of equivalent fractions: 50 over 100, 5 over 10, and 1 over 2. You can do the same thing with 6 over 8. You can see that you can divide both 6 and 8 by 2, and 6 divided by 2 would give you 3, and 8 divided by 2 is what gives you 4. Many times they're going to organize this information into tables. You can see that tables are simply used to organize data to make it easier to find relationships between the two. So here, this table is showing girls to boys. They're doing free throws, which they're counting the number of free throws made in PE class. So you can see basically for every 3 free throws made by the boys, the girls made 2. And it seems consistent as you go forward. The next 3 means there was 6 made by the boys, and then the next 2 means there was 4 made total by the girls. And you can see that there's a consistent pattern here. You will learn later on that that's a linear pattern. Okay, that means it makes it easy to predict on down the line how many would be made after so many attempts. All right, and what they're going to ask you to do is a little bit of that work, which is mainly completing a table based off of what you're looking at. So in this example, Sean went on a bike ride in his neighborhood. During the ride, he saw 1 cat for every 3 dogs. So it wants us to finish filling out the table based on the above information during his ride. So you can see here they've already done part of this for us. We see that 3 to 6, when he saw 3 dogs, he saw 1 cat. The next, on the next 3 dogs, that means that he would have seen 2 cats. So at this point, we can assume then the next is going to be 3 more. So 9 would be your next value here in the table for dogs, which means then what would have to be for the cats? Well, you can see the pattern simply going up by 1. So it would be 1, 2, and then of course 3. All right. So then to finish off the table, we're looking at then 3 to 6, 6 to 9. For the dogs, the next value would have to be 12. And then that would then put us, if we're looking at the pattern for the cats, at 4. Now, if we break this down and we put the number of dogs over the number of cats, we get the following. We get 3 over 1, which is equal to 6 over 2, which is equal to 9 over 3, which is equal to 12 over 4. And these are all what we call equivalent ratios or equivalent fractions. You can also flip these over. If you flip them over, it would be 1/3, or 1 to 3, 2 to 6, 3 to 9, and 4 to 12. Now what I want you to notice is how, when simplified, all of these revert back to that initial beginning ratio or fraction. Okay, 12 over 4 is 12 divided by 4, which equals 3. Same here with 4 over 12. In the second example, 4 over 12, when simplified, ends up being 1/3. Each of these will do the same. All right. Then the last thing they may ask you to do is to complete an entire table based off that same concept of linear relationship. So in this example, Coach Pryor is able to grade 3 tests for every 2 tests graded by Mrs. Pryor. Create a table to show the relationship between how many tests can be graded by each. Well, we have the table already created here, so let's go ahead and fill in our values. It says that Coach Pryor is able to grade 3 tests to every 2 tests by Mrs. Pryor. Okay, and that is going to be consistent unless they say otherwise. So we can go ahead and fill each of these in one at a time, or you can do them back and forth. That's completely up to you. I'm going to go ahead and do one at a time. I'm going to start with Coach Pryor. So that's going to be 3. So the next value, if we're talking about 3 more, would be 6. And then the next value, if we're talking about 3 more, is going to be 9. And then finally, 12. As far as the number of tests that Mrs. Pryor can grade, it would be 2, then 4, then 6, and then 8. So again, if we analyze what we're looking at here, each of these being equivalent ratios, we can set it up as the number of tests that Coach Pryor does over Mrs. Pryor, which would be equal to 6/4, 9/6, and then finally 12/8. Each of these, 6/4, 9/6, and 12/8, simplify back to 3/2. And just as we showed you on the last example, you can take the same values and flip them over. 2/3, 4/6, 6/9, and 8/12. And again, each of these will all simplify back to 2/3. And that is how to finish and create tables using equivalent ratios.